In this lecture, we'll be discussing problems concerning the previous lecture's formulas. Let's have a look at the first problem. An elementary doublet is 8 centimeters long. If the 20 megahertz current flowing through it is 3 amperes, what is the field strength 25 kilometers away from the doublet in the direction of maximum radiation? So obviously, the problem here is finding the electric field strength of an elementary doublet. So we write down the formula. E is equal to 60 pi times I times L times sine theta divided by lambda r. Now, every variable in this formula is given in the question except for theta. But it is stated in the question that we are supposed to find the field strength in the direction of maximum radiation. So to get the direction of maximum radiation, sine theta must have its maximum possible value. So in order for sine theta to have the maximum possible value, theta should be equal to 90 degrees, so that sine theta would be equal to 1. Anything other than 90 degrees would produce a value less than 1. So now we plug everything in this given to our formula. So we have E is equal to 60 times pi times 3 times 0.08. This is the centimeters times sine 90 degrees divided by r lambda, which is equal to the speed of light divided by the frequency. So we have 3 times 10 raised to the 8 divided by 20 times 10 raised to the 6 times 25 kilometers. So calculating this, we'll get the electric field is equal to 120.64 microvolt per meter. Next problem. Calculate the radiation resistance of a half-wave dipole antenna 0.5 meters from one end at 300 megahertz. So in this problem, the feed point is no longer at the center of the antenna, but it is moved 0.5 meters from one end. So in order to solve for the radiation resistance, we have to use this formula. R sub x is equal to 75 divided by sine pi x over lambda quantity squared. X here is the distance. So in order to solve for this, we plug in all the values in the given to our formula. R sub x is equal to 75 divided by sine of pi times 0.5, this is the distance, divided by r lambda, 3 times 10 to the 8 divided by 300 mega, and then quantity squared. So we have r sub x is equal to 75 ohms. Now let's try to solve a problem involving a helical antenna. Find the gain and beam width of a helical antenna with a turn spacing or pitch of 0.13 meters and a diameter of 797.88 millimeters, transmitting a 1.2 gigahertz signal if the total number of turns is equal to 12. So what is being asked in this problem is the gain of the antenna and its beam width. Now let's try to solve first the gain. Let's write down the formula for the gain of the antenna. So gain is equal to 15 times pi times the diameter divided by the wavelength. Now quantity squared times n, which is the number of turns, times s, the pitch, divided by, again, the wavelength. So this is pretty much straightforward. All of the variables are in the problem except for the lambda, which we can obviously compute. So we just plug everything in to our formula like this. Now, careful, take note of the units. Make sure it is consistent. In this case, I've converted all units to meters so that everything would cancel out. And then after solving this, we get the gain is equal to 9409.59. Now, if you want to convert this to decibel, all you have to do is get its logarithm. So the gain in decibel is equal to 10 times the logarithm of this 9409.59. So that's it. That's it for the gain. And for the beam width, first let's write the formula for the beam width. It's theta is equal to 52 times the quantity of lambda divided by pi times d times the square root of lambda divided by n times s. And so we plug again all the given into our formula. Now the variables in this formula is the same as the variables in the gain. So actually you can just copy and paste all of the given and place it to the respective variable. And then after calculating for this, we have the value for theta. It's equal to 2.074 degrees.